Hi there, this is Heath. We're starting section 15.2, which is a section on double integrals over general regions. When I talk about a general region, what I mean by that is where the base of the shape is no longer a rectangle. And so when we are looking at the boundaries of our integrals, they're not going to be simple constants. Example 1 is going to start us out with just an ugly region. Let's go ahead and get started with that one. All right. So, excuse me. Not all the volumes we want to calculate have rectangular bases. In this section, we want to compute double integrals over more oddly shaped regions, like this one here. All right. We would like to find the volume of the solid, and I have left out some words here that I want to discuss, in the first octant, whose base lies between the parabola y equals x squared and the line y equals 4. The first octant in three-dimensional space is like the first quadrant in two-dimensional space. It's the quadrant where x is positive and y is positive and z is positive. Okay? And so we're looking at just the first octant here between the parabola y equals x squared, that's down here, the line y equals 4, that's right here. You can almost see the 4 peeking out on the y-axis there. There's the 5, but you can almost see the 4 there. And then this surface that's above it, that's z equals x squared plus y squared over 8. Okay? Irregular region, there's not an easy way to calculate this using just plain old geometry. But we can calculate the volume using calculus. Okay? The first step of the process is to sketch the base of the shape in the xy plane. You will want to be able to do this at least in your head, if not actually on paper. But the base included the parabola y equals x squared, and then the horizontal line y equals 4. If we had not said the first octant, it would have gone around to this side as well, but we're only looking at this side. Okay? So this is the shape that we're looking for. All right. I'm going to need this shape on the next couple of slides, which means I just have to keep redrawing it, but I'll do that. We've got a picture of what the base looks like. Now we have to choose which order do we want to set up the integral. Do we want a dx dy at the end, or do we want a dy dx at the end? I want to emphasize this. Either order is correct. There is no mathematically wrong answer. But a lot of times one order will be simpler to work through than the other. We'll see some examples later on where one order is going to be a lot harder than the other one. The other one will be hard, one will be easy. Okay? All right. In this example, we want to choose the order dy dx. And so this is what our integral looks like. Figure out what limits of integration we want to use. Okay. So we will start by setting up the outside variable. So there we go. Set up the outside variable first. And then we set up the inside variable. Okay. All right. So we're going to set up the boundaries in the x direction. I'll draw the picture again and remind you what it looked like. That was the parabola y equals x squared. And the vertical line, or the horizontal line, y equals 4. That's a y. There we go. For the outer variable, we just want to find what the largest and smallest x values, there are in the shape. So what two constants will contain the entire shape? This is x equals 0. And since this is where y equals x squared intersects y equals to 4, the x coordinate is equal to 2 at that point. And so the x values go from 0 to 2. The outer boundaries will always be constants. Okay? We're just describing in very crude terms that this is a shape that starts at 0, ends at 2 on the x-axis. We're just defining some numerical boundaries. And that's all we're doing. The finesse comes on the inside layer. And that's what we're going to do for the inside now. So again, let's look at the shape. Y equals x squared. Y equals 4. And we've already said that the x coordinate goes from 0 to 2. All right. For the inside layer, we're going to write formulas. Imagine that we were an arrow traveling between the x boundaries of 0 and 2. We've already set up that the x boundaries are 0 and 2. And we're traveling into y direction. So I'm an arrow traveling into y direction. And I figure out, where do I enter the shape? I enter the shape somewhere along this curve. And this curve is y equals x squared. And now I travel through the shape, through the region that we're looking at, and I exit the shape along the region. I exit the region along the line y equals 4. All right. And the formula we're integrating is x squared plus y squared over 8. So the inner variable is formulas, and they can include the outer variable. That is, there's an x in his inner formula, but that's okay because now we're actually describing the contour of the boundary. On the outside, we're just describing the endpoints, 0 and 2, but on the inside, we're actually describing what that boundary looks like. The lower boundary is along y equals x squared. The upper boundary is along y equals 4. Okay? All right, let's work out this problem here. So we want to solve 0 to 2, integrate from 0 to 2, integrate from x squared to 4, x squared plus y squared over 8 dy dx. We start with the inner side integral. So when we start with that, the integral from x squared to 4 of x squared plus y squared over 8 with respect to y. X squared is just a constant, and so we just multiply by y. Y squared over 8 becomes y cubed over 24, evaluated from x squared up to 4. Oh, wow. Let's see. So when we plug in 4 for y, we're plugging in for y because this is our variable of integration here. This becomes 4 times x squared over 8, which is just x squared over 2, plus 4 cubed over 3. Is that right? No, 24. There we go. Integral of y squared over 8 is y cubed over 24. So we get 64 over 24, which simplifies to 8/3. Minus, now we're going to plug in x squared, so we get x to the 4th over 8. And plug in x squared here, we get x to the 6th over 24. All right, now we integrate that from 0 to 2. x squared over 2 plus 8/3 minus x to the 4th over 8 minus x to the 6th over 24 dx is x cubed over 6 plus 8x over 3 minus x to the 5th over 40 minus x to the 7th over 168. Plug in 2 and plug in 0. And at this point, we're looking at a calculator problem. When I plug in 2, I get 8 over 6 plus 16 over 3 minus 32 over 40 minus 128 over 168 minus 0. And in the interest of time, I'm not going to take the time to calculate this. I'll let you work through the calculations. Ha ha ha. Sorry. You can work through the calculations and get a volume for this, but this is the volume of the solid that we've been looking at. I want to emphasize before we move on that when we set up the integral, we set up the outer boundaries first because they're just constants. They're easy to set up. And then once we have the constant set up, we set up the inside boundaries. But then when we go to solve the integral, we solve the integral from the inside to the outside. So we set it up outside to inside. We solve it inside to outside. Let's move on. Let's calculate this integral here. Sine of x over this region. R here is the region bounded by the x-axis. So here's the x-axis. And a line y equals x. And a line x equals 1. And so we're looking at this as our base. And this is the function, the z value, that we're integrating over. Okay? So the first thing we have to do is we have to choose an order. Do we want to do dx dy or dy dx? And mathematically, there is no wrong answer. But when I look at this, and I think about what it takes to integrate sine of x over x, that's a messy integration by parts problem. I don't even know if we can do this by integration by parts. This is going to be a messy integration if we integrate with respect to x. But if we integrate with respect to y, it's super easy because this is a constant with respect to y. And so I would rather this first integral be with respect to y and then cross my fingers and hope that something cancels before I actually have to go around and integrate it with respect to x. So I am choosing to integrate with respect to y first to see if that will make the problem simpler. Okay? All right. So now we're going to set up the integral. In the x direction, we just want crude boundaries. We just want to know what is the smallest x value and the largest x value that contain this shape. And those are 0 and 1. In the y direction, we pick an arrow that's traveling between 0 and 1 in the y direction. And see where we enter the shape. We enter the shape right here on the x-axis, which is y equals 0. and we leave the shape along this diagonal edge, which is y equals x. Okay. Traveling in the y direction, the lower boundary is y equals 0, the upper boundary is y equals x. All right. Now let's try to solve. We start with the inside integral. Again, with respect to y, this is easy to integrate. It's sine x over x times y, going from 0 to x. So when I plug in x for y, I get sine x over x times x. Then I plug in 0, sine x over x times 0, and that just equals sine x. The x's cancel here, and 0 kills everything there. And so we integrate now from 0 to 1, sine x dx. See how much easier this is than that original problem would have been. By integrating with respect to y first, and then plugging in that x, something canceled and simplified the problem. Well, we can integrate this. The integral of sine of x is negative cosine of x from 1 to 0. And so we get negative cosine of 1 radian. We have to do this in radians now because this is calculus. Minus a negative cosine of 0. Minus a negative is plus, and cosine of 0 is 1. And so we get 1 minus cosine of 1 radian. Okay? All right, that's example 2. Let's move on. Let's try this problem. This is just a setup question. Let's set this up. Let R be the region enclosed by the graph y equals 4 minus 2x. That's a line that has a y-intercept of 4 and a negative slope of negative 2. And it crosses down here at x equals 2. And then the other two boundaries are the x-axis and the y-axis. So this is just this triangle right here. Question says to set up a double integral to determine the volume if z equals x squared over this region in the order dy dx. So my function that we're integrating is x squared. The order we're integrating is dy dx. We have to figure out how to set this up now. We start with the outside, and we just give crude boundaries for the outside. We just want a numerical, what is the smallest x value and what's the largest x value that will contain this shape. So the shape is contained between x equals 0 and x equals 2. And then for the y direction, here's where we actually describe the contour. We travel along an arrow in the y direction between 0 and 2. See where we enter the region. We enter the region along this horizontal line, which is y equals 0. And we leave along this diagonal line, which is 4 minus 2x. And that's the setup for this problem. Okay. Well, this is part A. Part B says to try that same setup again in the opposite order and see what happens. So let's do that, okay? All right. So same base. This is y equals 4 minus 2x. Crosses up here at 4, down here at 2. We want to integrate, the function is still x squared, but this time we want dx on the inside and dy on the outside. So now we want crude numerical boundaries in the y direction. what are the largest and smallest y values that contain the shape, without regard to any description of the contour. The shape lies between 0 and 4 on the y-axis. And now, if I were an arrow traveling along the x direction between 0 and 4, I enter the shape along this vertical line, which is x equals 0, and I enter the shape along this diagonal line. But I have to be careful because I have to represent this in terms of x. And the diagonal line is y equals 4 minus 2x. But that's the same thing as 2x equals 4 minus y, or x equals 4 minus y over 2. And that's what I have to use for my boundary here. I have to describe this diagonal line. I have to describe what x equals to along the diagonal line. And x equals to 4 minus y over 2. And so this integral and the one on the previous slide were both describing the exact same volume. Both will give you the exact same numerical answer, but one may be a little bit easier to work out than the other. Okay? So let's keep going. How do we reverse the order of integration? When I say reverse the order of integration, I mean, can we set up a double integral in a different order than the one that's given? We have a theorem, it's Fubini's theorem, we talked about that on Friday, that says if the boundaries are constants and the function is continuous, then we can just reverse the integration willy-nilly and there's no problem. But if the integrations are not constants, we're still allowed to reverse the order of integration, but we have to set up the new integral to reflect the correct geometry. So we have to now solve for the new limits of integration. We can't just switch the order. Excuse me. So let's try this example here. We're going to sketch this graph, sketch this region, and then switch the order of integration. So we want to end up with something where we're integrating the same function 4x plus 2, but we're integrating in the order dx dy. All right. So let's draw what this is. My boundaries are y equals 2x, y equals x squared, and x equals 0 and x equals 2. So the crude boundaries are just 0 and 2. The shape lies between these two vertical lines. The upper boundary is y equals 2x. That's a straight line with a slope of 2. And it goes through y equals 4 up here. When x is equal to 2, then 2x is equal to 4. The lower boundary is y equals x squared, which is a parabola that curves up and then hits y equals 4 also. Okay, we can check this. If this is the region we're looking at, the x coordinates go from 0 to 2, and if I'm an arrow traveling in the y direction, I will enter along the parabola, which is x squared, travel through the shape, and then leave along the diagonal line, which is y equals 2x. So this sort of bean-shaped region here is what we're looking at. So if we set it up in the opposite order, dx dy, I want numerical boundaries for y, What are just the largest and smallest y values we can have? Those are 0 and 4. And then if I take an arrow between 0 and 4 and enter the shape, notice that in the x direction, we're entering the shape along the diagonal line instead of along the parabola. And so while the line was on top in the y direction, the line is going to be on the bottom in the x direction. But I have to take this line and express it as a function x equals something. So x equals y over 2. It's going to be my lower boundary. Then we travel through the shape and we leave along the parabola. And again, I need the parabola in the form x equals something. So x is going to be square root of y. And then this is the exact same problem as this. These are equal to each other. But the top one looks like it might be a little bit simpler to work out than the bottom. Okay? All right. Okay. Let's move on. Let's try this problem here. We would like to evaluate this integral here from 0 to 1, square root of x to 1, square root of 1 minus y cubed dy dx. So the hard way is to just dig in. And we have to integrate from square root of x to 1, square root of 1 minus y cubed dy dx. Well, how do we do that? We can't do u substitution. If we let u equal 1 minus y cubed, then dy would be 3y squared dy, or du would be 3y squared dy. I don't have a y squared out here. I can't factor this easily. It factors into 1 minus y times, what is it, like 1 plus y squared plus y, or 1 plus y plus y squared. That doesn't help me very much. I don't see an easy way to use integration by parts. How do we do that? This is horrible. This is a messy, messy integral that I don't know how to do. But it's an easy integral if we integrate with respect to x, because, once again, there is no x in this term. And so if we integrate with respect to x, it's just like integrating a constant. So let's try this problem in a different order. Try changing the order. Yeah, let's see if this works, okay? All right. So let's sketch this region here. My boundaries are y equals 1, y equals square root of x equals 0, and x equals 1. All right. So the x boundaries are 0 and 1, and the y boundaries are y equals 1. That's just a horizontal line. And y equals square root of x, the square root function goes like so. And in the y direction, we enter along the square root, and then we go up, and then we leave along y equals 1. So it's the region between the square root and the 1. All right. So how do we set this same problem up in this order here? Okay. So now I want to put numerical boundaries on the outside, the smallest and largest y values in the region. And then if I were an arrow traveling between those boundaries in the x direction, I enter the shape along this vertical line, which is x equals 0, and leave the shape along this curve. That's this curve right here, but I have to express it as x equals to something. So x equals to y squared. Okay. All right, let's try solving this. So we solve the inner side integral first. 0 to y squared, square root of 1 minus y cubed dx. Well, this is a constant with respect to x, so it's just square root of 1 minus y cubed times x, evaluate at 0 and y squared, which is square root of 1 minus y cubed times y squared minus square root of 1 minus y cubed times 0. And that's just the square root of 1 minus y cubed times y squared. Now, if we integrate that from 0 to 1, this is a u substitution problem. If I let u equal 1 minus y cubed, then du is equal to 3y squared dy. And so 1/3 du is equal to y squared dy. And so we get the integral of square root of u du. There's a 1/3 that we'll put out front. And my boundaries have changed. When y is equal to 0, u is 1 minus 0. And when y is equal to 1, u is 1 minus 1. So my boundaries switched from 0 on the bottom and 1 at the top to 1 on the bottom and 0 at the top. All right, well, the integral of square root of u is u to the 3/2 times 2/3. And there's also a 1/3 out here, times 1/3. Plug in 0 and 1. Okay. And let's see what we get. We get 0 minus, let's see, there's a negative sign here that I've dropped. If u is 1 minus y cubed, du is negative 3y squared. There's a negative 1/3. There's a negative here. And so this is 0 minus a negative. That's what I was missing. 1 times 2/3 times 1/3, which is equal to positive 2/9. I knew the final answer had to be positive. I'm sorry, I realized I made a sign mistake right there. Okay. This wasn't an easy problem even after we changed the order. We still had to do a u substitution, and I almost messed it up by forgetting the negative sign. But then, managed to recover. But it was a lot easier to integrate it in this order than it was in the original order. Okay? And so that's sort of the takeaway that I want you to focus on while you're working on these WebAssign problems for this section, is to think about which order is advantageous for you when solving a problem. And if it's not in the order that's best for you, how do you switch the order so that it is better? Okay? Being able to be flexible about changing the order avoids you ever having to get stuck in this kind of situation here. All right. Well, have a great couple of days. See you again on Wednesday.